When they are first created or modified to ensure that the sequence of operations and motions are correct. Whether programming the control or just verifying a CAM-generated part program, graphic verification systems are valuable visualization tools. VANUC's Manual Guide I conversational programming system provides advanced 3D solid model animation to fully visualize the tooling and the part being machined. Many machine tool builders provide Manual Guide I with their machines, and it can be used to animate standard G-code programs. 3D solid model animation requires a little more information than is typically in a G-code part program, but the modifications required can be quickly achieved with 5 simple steps. First, open the G-code program in Manual Guide I. Second, define the workpiece blank. Next, define some additional tool data, and then activate tool radius offset values for each tool. Finally, you can run the animation. Step 1. Open the program in Manual Guide I. If the G-code program is already active in the CNC, you simply need to switch to Manual Guide I. For this demonstration, we will first switch to Manual Guide I and then open the G-code program. Start by selecting Edit Mode. Next, activate Manual Guide I. Each machine tool builder can customize how Manual Guide I is activated, so check with your machine documentation. In this NC Guide CNC, it is activated by pressing the Graph button on the MDI panel. Next, press the O-List soft key to show the available part programs, and use the cursor keys to highlight the required program. Finally, press the Open soft key. The program is now displayed in the editor, and you're done with Step 1. Step 2. Define the workpiece blank. Solid model animation requires a blank geometry, so it can show the tools machining the material. The part program origin with respect to the blank must also be specified. A special set of blank definition G-codes are available that can be programmed manually or using a CAD/CAM post-processor. However, we will demonstrate specifying the dimensions using conversational screens in Manual Guide I. Make sure the cursor is highlighting the first line in the part program. Press the continuous menu key until the Start soft key is displayed. Next, press the Start soft key. Press the right cursor key until the blank tab is highlighted. Manual Guide I can process several standard blank shapes, including a rectangle, a cylinder with a hollow center, a prism with a hollow center, and a free contour cylinder. Use the cursor down key if necessary to highlight rectangular blank figure. Now press the Select soft key. In this demonstration, the blank is a rectangle 3.5 inches wide, 2.5 inches deep, and 0.75 inches high. Notice the graphic on the right will change as we move from field to field, guiding you with the required information. For the first field, the width dimension B is highlighted. First, enter the blank width in the x-axis and press the input key on the MDI panel. In this example, the width is 3.5 inches. The graphic changes again to prompt for the blank height in the z-axis. The height of the blank is 0.75 inches. That completes defining the material blank size. Next, specify where the part program 0 is in relation to the part blank. First, specify the work origin in X. In this example, the program 0 in X is the left of the part, so the value is 0. Just press Input or cursor down to select the next field. Next, specify the origin in Y. In this example, the program 0 in Y is at the back of the part, not the front edge. So based on the graphic, we need to add a value equal to the depth of the part blank, 2.5 inches. Finally, specify the work origin in Z. In this example, we will face the surface of the part, so the program 0 point is 0.02 inches below the surface of the blank. To complete the operation, press the Insert Soft key. Note that a G1902 block has been inserted into the program, and the parameters are the values from the conversational screen. This completes Step 2. Step 3. Define the tool data. Part programs typically use tool offsets to define the basic tool geometry to compensate for the tool length and the tool diameter when machining. To display the tool and its effect on the material more realistically, 3D solid model animation needs additional information. The example uses 7 tools, 5 drills, and 2 end mills. We will start with a procedure for entering tool offset and tool data information for a drill. Press the continuous menu key until the T-offset soft key is displayed. Press the T-offset soft key. There are 2 tabs for tooling. The Offset tab displays the same data as the standard tool offset pages. There are columns for tool wear and tool geometry for both the tool length and the tool radius. The Data tab displays new information about the tool. This includes the tool type, which can be drill, chamfer, end mill, ball mill, tap, reamer, boring, or face mill. And the set of the tool, which is the orientation of the tool in the tool holder. Note when the drill type was selected, an additional column is displayed for the point angle. With the Offset tab selected, cursor down until the appropriate tool number is selected. Use the cursor right key to select the Cutter Compensation Geometry field. Enter a tool radius and press Input. Note, if you have the tool's diameter, you can calculate the radius by entering an expression in the fields. Enter the diameter followed by the backward slash for divide, and then a 2, and then press the Input key. For example, for tool number 2 in our example, enter 0.213 divided by 2 and press the Input key, and the correct radius of 0.1065 is registered. Press the cursor right key on the MDI panel until the Tool Data tab is displayed and the Tool Type field is highlighted. Press the Drill soft key. Press the cursor right key until the Set field is highlighted. A drill can have 4 different orientations depending on the machine type and tool holder orientation. Enter the orientation and press the Input key. In the example, we'll be using a conventional drill in a vertical machining center, so the orientation of our drill is 1. Press the cursor right key until the nose angle field is highlighted. Enter the nose angle from the manufacturer's datasheet and press the Input key. For a drill, the nose angle is the drill point angle, which is 118 degrees. Repeat these steps to define any additional drills. You may prefer to enter all the data on the Tool Offset tab before entering the data on the Tool Data tab. It's just a personal preference. Entering tool data for an end mill is a similar procedure, except there is no nose angle data. First, select the tool and enter the tool radius information. For an end mill, press the F-end soft key. The orientation selections are the same as for a drill. Select Orientation 1. Repeat the steps for additional end mills. When all of the tool data is entered, press the Close soft key. That is the end of Step 3. Step 4. Activate radius offset for each tool. Typically, there's no need to activate tool radius offsets when the cutter radius offset is not used, for example, when performing drilling operations. However, Manual Guide I must know the tool radius to correctly animate the tool and the material remove. For a Machining Center program, we must include a D word at each tool change. Because the cutter compensation is not activated with a G4142, it has no effect on the program path. Typically, this edit is not required for turning applications. Press the continuous menu key until the search down soft key is displayed. With the cursor at the start of the program, enter MO6 and press the search down soft key. If a D word is not programmed, insert the appropriate D word value for the active tool. For example, if T11 is active, add D11 to the MO6 block. Move the cursor to the word prior to the end of the block, enter the letter D followed by the tool number, and press the Insert key on the MDI panel. Press the Search Down soft key again. Insert a D word value for the active tool if required. Repeat this procedure for all the tools in the part program. When the message Searching Characters is not found is displayed, all the tools have been modified and Step 4 is complete. Step 5. Run the animation. Press the continuous menu key until the Simulate soft key is displayed. Press the Simulate soft key. Press the Rewind soft key to rewind the program back to the beginning. Press the Start soft key. The animation will begin at an accelerated rate until machining is complete. At any time during the animation, you can press the Pause soft key to stop the animation. You can step through sections using the single soft key, or restart the animation by pressing the Start soft key. If you want to see the toolpath, press the Toolpath soft key and press the Start soft key. There is the added benefit of seeing the toolpath within the wireframe of the part blank. If the animation runs too fast for your liking, parameter 27335 can be used to set the number of speed steps. Setting the parameter value to 9 provides 9 speed steps. Now 2 new soft keys appear on the Animation menu. The Speed minus soft key will slow down the animation, and the Speed plus soft key will speed up the animation. Step 5 is now complete. We have seen how any standard G-code program can be modified to run in solid model animation in just 5 steps. Open the G-code program in Manual Guide I. Define the workpiece blank. Define some additional tool data, and then activate tool radius offset values for each tool. Finally, you can run the animation.